Hello students, today we'll be starting with the first chapter of class 10 CBSE mathematics known as real numbers. Now real numbers is a chapter which focuses on the nature of numbers. What do we mean by that? You might recall in junior classes you studied integers, fractions, decimals, rational numbers, etc. etc. So when we say nature of these numbers, we mean what are their unique properties, their specific properties, and how can we use them to prove some basic things in mathematics. The chapter is divided into 4 major sections, starting with integers. We'll study the basic properties of integers, how we define them, and how we use this definition to prove certain things. After integers, we'll move on to the use of Euclid's division algorithm. Euclid's division algorithm is connected to integers, but it's an application-based part of the chapter. After we're done with integers, we'll move on to rational numbers. Once again, their definition and how we use them. And finally, its partner, irrational numbers. Those numbers which are not rational. And how do we prove that a number is not rational? So these are the 4 major sections. So let's dive into integers. So let's begin with integers. You might remember integers are just our basic numbers, meaning if we draw our number line, our integers are nothing but 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, so on in both directions, as well as of course the number 0. Now as a basic concept, this is very simple, it's very straightforward. But let's define an integer algebraically and using this definition prove some interesting questions and concepts. So Euclid, a mathematician we've encountered before in class 9, Euclid is a person who created a concept known as Euclid's division lemma. Euclid's division lemma said that if a and b are 2 positive integers, then assuming a is greater than b, we can represent it like this. A is equal to b multiplied by another integer q plus an integer r. This r is known as our remainder, and the condition is that r should be less than b. Using this definition of integers, we can define integers according to how it's convenient for us. So an example of Euclid's division lemma is that the number 5. 5 is equal to 5 into 1 plus 0, 4 into 1 plus 1, 3 into 1 plus 2, 2 into 2 plus 1, because if I do 2 into 1 plus 3, 3 is greater than 2, so not allowed, has to be less than 2. 2 into 2 plus 1, and of course finally with 1 into 5 plus 0. Now using this concept, we can break up our numbers according to a definition that we like. For example, we know we have even numbers and we have odd numbers. We can say that all even numbers are of the form n is equal to 2p, where p is any other integer. Because obviously 2p is divisible by 2, meaning it's an even number. And an odd number can be represented as 2p plus 1. Because now we can see this is not divisible by 2. It will leave a remainder of 1. So hence defining numbers using Euclid's algorithm or Euclid's definition helps us understand what is a number, an integer, and how can I represent them. So let's see how we can apply this concept in some questions. So now let's see how we can use Euclid's lemma and the way we define integers to solve our questions. Now we've seen that any integer a can be represented in the form bq plus r, where a, b, q and r, we're saying for positive integers of a and b, all of these should be positive numbers, with b theoretically being less than a, otherwise it doesn't make sense, q would be 0. So the way we'll use this to prove questions is, we can see that if I fix my b, given that r has to be less than b, we can see that we can define an integer according to this b. We can fix the number of definitions. What I mean by this is, let's assume b is equal to 3. Now we know that r has to be less than b. So since r is less than b, these 3 dots mean since. This means that in this particular case, r is less than 3. R is also supposed to be a positive integer or 0, which means r can be equal to 0 or 1 or 2. Meaning that when my b is set to be 3, every integer is of the form 3q plus 0 or 3q plus 1 or 3q plus 2. And if you think about it, if you pick any integer in your mind and divide it by 3, you will see either it will leave no remainder, meaning it's a proper multiple of 3, or it will leave the remainder 1, or it will leave the remainder 2. So I can show that every integer is in this format, and using this definition based on the question, we can prove various things in algebraic mathematics. So let's look at one of these types of questions. So let's say that this is the question. Prove that every odd number is of the form 4p plus 1 or 4p plus 3. So what this question is telling you is that we have to prove that if a number is odd, it can be written as either 4p plus 1 or 4p plus 3. Let's just take two random numbers. 5. 5 is 4 into 1 plus 1, meaning it is satisfying 4p plus 1, here p is equal to 1. And the number 7, 7 is 4 into 1 plus 3, 4p plus 3, again p is 1. And you can check for yourself, pick any odd number, divide it by 4, see what the remainder is. It will always either be 1 or 3. But how do we prove this? The key is the 4. Since we're talking about 4, this is our b in our Euclid's division lemma. So I will say any integer a or every odd number, when we say odd number in this case we mean integer, any integer a will be of the form 4p plus, now we know r, so either 4p plus 0, which is nothing but 4p, or 4p plus 1, 4p plus 2, 4p plus 3. These are what all my integers a can be defined as if b is 4. Now, what is the definition of an odd number? An odd number is equal to 2p plus 1, again where p is any integer, because this means it's odd, not divisible by 2. So we will manipulate these and show that they can be brought to this format. Now observe, what is 4p? 4p can be written as 2 multiplied by bracket 2p, which can be written as 2q. Q is just another integer equal to 2p. Obviously, this is an even number. What does that mean? An odd number cannot be of the form 4p. Now let's check 4p plus 1. Again, this can be written as 2 into 2p plus 1, which is equal to 2q plus 1. Here, q is equal to 2p. Now, 2p plus 1, 2q plus 1. Don't focus on the variable. Focus on the fact that it's 2 multiplied by an integer plus 1. So, odd number. This is even, this is odd. What about 4p plus 2? Now, if you observe, I can take 2 common. We'll be left with 2p plus 1. This is also an integer, can be replaced with 2q, again even number, where q is equal to 2p plus 1. And now 4p plus 3 can be written as 4p plus 2 plus 1, simply breaking my 3 into 2 plus 1. We already know that 4p plus 2 can be written as 2 into 2p plus 1, 2 into 2p plus 1 plus 1. Once again, this is an integer, can be written as q. So I have 2q plus 1, and here again q is equal to 2p plus 1. This once again is an odd number. So we can see my integer has to be one of these 4 types. Of these 4, 4p and 4p plus 2 will always be even. 4p plus 1 and 4p plus 3 will always be odd. Hence, a number, an odd number, must be of the form 4p plus 1 and 4p plus 3. This is what we mean by proving integer questions using Euclid's division lemma. Let's look at a slightly more complicated example and then move on to the next topic. So now a slightly more complicated question. This time we have to prove that the cube of any positive integer is of the form 9m, 9m plus 1 and 9m plus 8. Now if we go by the logic of the previous question, b is 9, but if you take b to be 9, there will be 9 cases, r equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. That will be much too long. So let's think. A factor of 9 is 3. In fact, 9 is 3 square. So let's try and prove this question taking our b to be 3. Now if our b is 3, that means our integer is of the form 3q plus 1 or 3q plus 2. Now we're talking about the cube of any positive integer. So let's cube all of them. So this is of course our 3 integers. Now 3q cubed is very straightforward. 3 cubed and q cubed. So this is equal to 27 q cubed. Observe, this can be rewritten as 9 into 3 q cubed, which is nothing but 9m, where m is equal to 3q cubed. As I said, we don't care about what m is, what q is, what p is. They all just represent a positive integer. So obviously 3 is a positive number, q is a positive integer, so 3q cubed will also be a positive integer. So I simply replace it with m. Now 3q plus 1 whole cube. So to open it up, we'll use a plus b whole cube formula, which is a cube plus 3a square b plus 3ab square plus b cube. I'll write it here. A cube plus 3a square b plus 3ab square plus b cubed. So first term cubed, 3q cubed, we already know that, 27q cubed, plus 3 multiplied by a square, which is 9q square, multiplied by b, this case is just 1. So 3 into 9q square, 27q square, plus 3 into 3q into 1 square, now 1 square is just 1, 3 into 3q, 9q plus 1 cubed, which is simply 1. Now from these 3 I can take 9 common. It will become 9 into 3q cubed plus 3 cubed squared plus 3q, just plus q plus 1, because 9 into 3q cubed is 27q cubed, 9 into 3q squared is 27q square, 9 into q is 9q. This is a positive integer, positive integer, positive integer. Their sum will be a positive integer. I can replace it with 9m plus 1. Second format. Opening this one up, same way. First is just 27q cubed. Second is going to be 3 into 3q whole squared into 2 this time instead of 1. So 54q squared plus 3 into 3q into 2 squared this time instead of 1 square. So 9q into 4, 36q plus 2 cubed, 8. Once again, I can take 9 from here, 9 from here, 9 from here. I'll be left with 9 into 3q cubed plus 6q squared plus 4q plus 8. Again, positive integer, positive integer, positive integer. The sum will be a positive integer, can be replaced with m. So we can see integer has to be either 3q or 3q plus 1 or 3q plus 2, which means their cube has to be 9m, 9m plus 1, 9m plus 8. So like this, when you get a question about integers, in your mind, first figure out what is the b that I want. Write out all of the cases, case 1, 2, 3 in this case, when we did the 4 question, 4 cases. Do what is given in the question, manipulate your numbers and get to your desired result. So with this, let's move on to Euclid's division algorithm. So now let's look at calculating the HCF of two numbers in a new way. Now earlier, when we were in younger classes, I think all the way back to class 5 or 6 even, we learned that to calculate the HCF of two numbers, let's say 16 and 12, what would we do? We would write out their prime factors. 12 is 2 into 2 into 3. Every time a prime factor is common, we would circle it as a pair and we would simply multiply all the pairs. So the HCF of 16 and 12 would be equal to 2 into 2, 4. Now we learn how to calculate the HCF using Euclid in what we call Euclid's division algorithm. An algorithm is nothing but a set of steps that you can always follow to get an answer of a type of question. In other words, every HCF can be found following a certain set of steps. How do we do Euclid's division algorithm? Let's take 16 and 12 again. Which is bigger? 16. So we'll write 16. And we will write 16 in the BQ plus R form using the smaller of the two numbers. So 12 is my B. What do I multiply to get to 16? Only 1. If I multiply by 2, it will go over. 12 into 1, remainder 4. Since we still have a remainder, this means 12 is not dividing 16. 12 is not a factor of 16. 12 is not the highest common factor. Now, we take the B of this step and write it. Now, it becomes our first number, the A, and we'll write it in BQ plus R form using our remainder as B. So 4 multiplied by 3 to get to 12, and now look, 4 into 3 is exactly 12, so the remainder is 0. So what does this mean? 4 is dividing 12, and if we look over here, I can take 4 common here. It will become 3 plus 1, which means 4 is dividing 16. So therefore, following this algorithm, once you reach this position where your remainder is 0, that B value is your HCF. We can see HCF in both cases is 4. So we'll do one more example with slightly more steps because this happened in one step. So let's take the numbers 28 and 16, both in the traditional method and in the new method. 28, 2 into 2 into 7, 16, 2 into 2 into 2 into 2. Once again, 2 pairs of 2 common, HCF, 2 into 2, 4. Euclid's division algorithm. Bigger number is 28. 28 is equal to 16 multiplied by 1 again, 2 will become 32, plus 12, remainder is not 0. 16 with 12 as B, 12, now of course it's following this, into 1 plus 4, remainder is not 0, 12 is equal to 4 into 3 plus 0. So once again, 4 is our HCF. So in both cases, 4, 4. This is how to calculate the HCF from Euclid's division algorithm. Write the bigger number in BQ plus R form using the smaller number. If there's a remainder, now your B becomes your A, your remainder becomes your new B, and again BQ plus R form until the remainder is 0. When the remainder is 0, your final B value is your HCF. This is how we'll solve it like this. Let's move on to rational numbers. Now that we're done with integers, let's move on to rational numbers. Now, rational numbers, you might remember, are simply those numbers that can be represented as n is equal to p over q, where p and q are integers and q is not equal to 0, because obviously it will become divided by 0, which is not allowed. This is the simple definition of a rational number, and a rational number therefore is anything that can be represented like this. For example, the number 7. 7 can be written as 7 upon 1, it can be written as 14 upon 2, etc., etc. So I can see it is in p by q form. What about a decimal? Let's take 3.5. 3.5 can be written as 35 upon 10. I can simplify it to 7 upon 2, so on and so forth. Clearly it's in p by q form. Even some decimals that are not finishing, what we call non-terminating, 0.6666 so on. 0.6666 so on is nothing but 2 upon 3. So 2 upon 3, it is a p by q form. So it's a rational number. Like this, we are going to study how can we identify whether a rational number will have a terminating decimal like 3.5 or a non-terminating decimal like 0.66666. This is determined by our denominator in p by q form, its properties, and how we apply them. So let's look at these properties and how they work. So now we'll move on to rational numbers, solving questions. As we already discussed, any rational number, let's say n, can be written in p by q form, where p and q are integers and q is not equal to 0. What we're going to be focusing on is the decimal representation of rational numbers. Specifically, how can we calculate or figure out whether we'll have a terminating decimal, that means a decimal that's not going on for infinite number of times, and if it's terminating, how can we actually find it? There's a very straightforward rule. For a rational number to have a terminating decimal, our denominator q can only have the factors 2 and 5. It cannot have any other factors. In other words, q must be able to be represented in the form 2 to the power n, 5 to the power m, where n and m are integers. This simply means that when we write out our number in p by q form, when we bring it to its simplest fraction, your denominator should only have 2 and 5 as its factors. Let's look at how we apply this and how we can actually calculate it. For example, let us look at the fraction 12 by 18. Now, first things first is we will simplify this. What will we get? 6 divides both of them. 2 by 3. Is my denominator of this form? No, because 3 is also here. This will be non-terminating. What about a different case? Let's take a situation where we have something that initially looks like it won't be in this case, but when we do it, it will be 6 upon 30. Now if you just look at 30, 30 is 10 multiplied by 3. So 3 is a factor of it. But we can simplify this, right? 1 by 5. Now this is of this form because it's nothing but 1 upon 2 to the power 0, which is absolutely allowed because n and m should be integers, and 5 to the power 1. And we know that 1 by 5 is nothing but 0.2. So this way, very straightforward. Simplify your fraction. Your denominator should only have 2 and 5 as its factors in whatever power. Let's look at, for a very big denominator of 2's and 5's, what is the approach to finding the decimal value. Let's assume we have a scenario where we have to find the decimal expansion of 37 divided by 160. Now, first of all, 37 is a prime number. I chose it deliberately for this reason. So this will not simplify any further. Let's factorize our denominator. This is 16 into 10. 16 is 2 to the power 4. 10 is 2 multiplied by 5. So this whole thing is nothing but 2 to the power 4 multiplied by 2 into 5, which is 37 upon 2 to the power 5 multiplied by 5 to the power 1. Now observe something. If I make this 5 to the power 5 somehow, this will become 2 into 5 to the power 5. Powers become common if the bases become common if the powers are the same, which is 10 to the power 5, which is just a bunch of zeros. I can just then divide my number with its decimal place. So what we'll do is, our target is to convert this to get the 2 and 5 to have the same power. So if I want to multiply this by 5 to the power 4, that way it will become 1 plus 4, 5 to the power 5. I have to multiply my numerator also by 5 to the power 4. This way we can see that it becomes 37 multiplied by 5 to the power 4, 5, 25, 25 into 5, 125, 125 into 5, 625. Divided by, now this will become same base, powers get added, 2 to the power 5 into 5 to the power 5, which is nothing but 37 into 625 divided by 2 into 5 to the power 5, which is 37 into 625 upon 10 to the power 5, which is nothing but 1 followed by 5 zeros. So once I calculate this value, I can then simply shift the decimals, the number of zeros we have, standard decimal shifting. So we'll calculate over here 625 into 37, standard multiplication, 35, 14 plus 3, 17, 42, 43, 0 here, 15, 6 plus 1, 7, 6 into 3, 18, 5, 12, 11, 13, 23. So 2, 3, 1, 2, 5 divided by 1 followed by 5 zeros, which gives you your final answer. How many times will we shift the decimal? 5 times. Where? to the left. 1, 2, 3, 4, 5. 0.23125. This is how we come from a fraction to a decimal if it is terminating. We find the factors of the denominator, try to make the 2 and 5 have the same power, multiply accordingly, and then shift by the number of zeros. Last small thing in decimals is how to identify from a decimal whether we'll have a terminating or a 2 and 5 denominator or something else. Very straightforward. If the decimal is terminating, the denominator will be of the form 2 to the power n, 5 to the power m. If the decimal is not terminating, but it is repeating, what does that mean? Something like this, or something like this. We can see that certain things are repeating. This will be a rational number, but without a 2 to the power n, 5 to the power m denominator. Finally, if your decimal is neither terminating nor repeating, as in it doesn't follow any pattern, that means it is an irrational number. So if I just write any numbers randomly and keep going, no pattern is being followed, this means it is irrational. So now that we've understood what an irrational number is as a decimal, let's look at proving numbers irrational. Now we move on to the final part of the chapter, which is the partner of rational numbers, nothing but irrational numbers. Now, irrational numbers, as the name suggests, are those numbers which are not rational. In other words, they can't be represented as a fraction. So, what are irrational numbers? Have we encountered any irrational numbers so far in our studies? Yes, we have. In fact, the most famous irrational number is pi, what we use in our circles chapters. Now you might be confused, you might be thinking, but we say pi is 22/7, we say pi is 3.14. These are approximations. This is to make your job simpler, because you can't be calculating to 1000 decimal places. It's not reasonable. So we approximate the value to be 22/7 or 3.14. Pi is actually not a rational number. Similarly, we studied square roots and exponents. Now, the square root of 4 is 2 and -2. But we know that the square root of 2 is 1.414 ... This is an irrational number, because we will see that root 2 does not have a p/q form. So what we're going to study in this section is how can we prove that root 2 is irrational. We want to know for sure that it's irrational. And by extension, is it possible just by looking at the decimal expansion of a number that we can tell if it's rational or irrational? So let's see how we do these two things. So now let's look at the final part of the chapter, which is irrational numbers. As the name suggests, they are numbers that are not rational. In other words, they cannot be represented in p/q form. The standard question in this part of the chapter is to prove some root to be irrational. So let's do the most basic thing, which is prove root 2 irrational. The way we approach this is, we will do something known as proof by contradiction. So we'll assume that root 2 is rational. and then by manipulating it, we'll come to a case that shows that that's impossible. So assume root 2 is rational. This means root 2 is equal to p by q. I can rewrite this as root 2q is equal to p. Now I will square both sides. Square both sides. This will become 2q square is equal to p square. Here there's a small property you have to understand. Property states that if a prime number is a factor of the square of a number, in other words, if 2 is a factor of p square, it means 2 is a factor of p. So since 2 divides p square, it also divides p, means I can write p as 2 multiplied by some other number. So let p be equal to 2c. I'll replace it over here. This implies 2q square is equal to 2c whole square, which implies 2q square is equal to 4c square. 2 and 2 will get cancelled. I'll be left with q square is equal to 2c square. So once again, I have 2 dividing q square, which means 2 divides q. So 2 has shown up as a factor of p and a factor of q. But this is not possible because in a rational number, this p by q, they should have no common factors left. It's the simplest form. So this is a contradiction. 2 divides q. This is a contradiction. 2 cannot be a factor of both p and q. Hence, our assumption is not possible. So, by contradiction, root 2 is irrational. And this is how we will prove all questions with root involved in it irrational. You'll simply make it equal to p by q, you'll manipulate it, and you'll come to a point where you'll get this problem. So whether it is root 5, root 7, doesn't matter. The second type of question is they'll give you a root with a combination of integers, meaning they'll say prove 2 root 5 plus 3 irrational. In these questions, all you have to do is isolate your root number. It will come into some p by q form. We'll simply state that's not possible. Therefore, this also has to be irrational. So again, assume 2 root 5 plus 3 is rational. This implies 2 root 5 plus 3 is equal to p by q. First, I'll shift my 3 here. So it implies 2 root 5 is equal to p by q minus 3, which is equal to p minus 3q by q. Now I will bring my 2 into my denominator. This implies root 5 is equal to p minus 3q by 2q. Now observe, integer, integer, so the subtraction will be an integer. 2 multiplied by an integer is just another integer. So this is come into, let's say, m by n form, where m is equal to p minus 3q, n is equal to 2q. This implies root 5 is rational. But this is not possible. Hence, 2 root 5 plus 3 can also not be rational. Not possible implies 2 root 5 plus 3 irrational. So this is the basic crux of the chapter. This is everything that we will mostly be solving. You just need to have your concepts straight, keep your formulas in mind, and then just simply apply basic algebra. So with that, let's now look at the next chapter.